So we will get started. Hi, everyone. My name is Emily Leinbach, and I am the Director of Marketing here at Keystone. I'm so happy to welcome everyone to today's webinar, Responsible AI and the Legal Implications of Bias in Algorithms. We're going to try to get started right on time here, but first I wanted to go over a few housekeeping items. We have a lot of content to get through today with Junsu and Rohit, so we're going to try to keep our presentation to about 35 minutes so we can leave room at the end for about 5 to 10 minutes of Q&A. So if you do have any questions, feel free to add them in the Q&A box at the bottom of your Zoom screen. But otherwise, we'll kind of get started with a quick overview of Keystone. So before I introduce our speakers here, I wanted to share a little bit more about the firm. So Keystone Strategy is a leading strategy, economic, and technology consulting firm for those who don't know. And we are delivering transformative ideas from the tech industry to top law firms, government agencies, and global Fortune 1000 brands. Keystone leverages a triad of skills and its extensive expert network in providing end-to-end interdisciplinary expertise in technology, economics, and industry as they apply to large, complex, and important problems in either high-stakes litigation matters or other business strategies. So without further ado, I am thrilled to introduce today's speakers. Junsu Choi is an engagement manager here at Keystone, and he co-leads the information strategy, risk and regulation practice here, focused on responsible machine learning and issues around fairness, accountability, transparency, and ethics. Rohit Chatterjee is a partner here at Keystone, and he leads the firm's economic and technology advisory group and helped to co-found our K.ATS, Keystone Advanced Technology Services team, which is made up of data scientists and software engineers. And now I will hand it over to our speakers to share more about the topics today. Rohit?
Thanks, Emily. Welcome, everyone, and thank you for joining. We have an action-packed deck for you today, and so without wasting much time, let's get into it. In terms of agenda, I will kick things off by motivating the need for responsible AI by taking you through some real-world examples of highlights and lowlights of intelligent systems. Now, this section might scare you a little bit, and so to save us, we will have my colleague Junsu here, who will help us understand where and how to diagnose these systems, and finally, he will leave us with hope about upcoming regulations and actions that are attempting to address responsible AI for all of us. To take a step back, I wanted to take a short moment to introduce this particular Keystone team that works on many different technology-related problems for businesses and law firms. Junsu and I, as Emily mentioned, are both members of the Keystone Advanced Technology Services team, the K.ATS team, that comprises of computer scientists, computer engineers, software engineers, software developers, and we are really engaged in applying novel computer science techniques to solve a variety of interesting real-world problems. I've highlighted 4 such areas. First, we work on questions related to software economics and value. Similar to financial assets, technology has become an important enough digital asset that companies are demanding their own equivalent income statements or balance sheets for these assets. So by looking deeply all the way into the source code, we help organizations build these statements to measure, to grow, and manage technology and data in an efficient way within the organization. Number 2, we help people understand how a piece of technology or the technology as a whole was developed, and how does it actually work? We do this by doing deep dive forensics and investigations in either a piece of technology or a product. Now, this may involve techniques like ethical hacking, reverse engineering, man-in-the-middle type of attacks, etc. Third, we help organizations with all things machine learning. Topics of fairness, accountability, and ethics are dealt with on a regular basis for our clients. And today's topic is a result of some of that work. Finally, we also work on data security and risk, where we help our clients deal with issues involving algorithmic privacy, cybersecurity threats, etc. To do this, we are very, very fortunate and lucky to have a great set of collaborators, either from academia or from industry, and a world-class infrastructure to help process these large data sets in a pretty secure environment. With that, let's get into responsible AI. So it won't be surprising to you when I say that the capabilities of machine learning and deep learning models have been evolving at a rapid pace in the last few decades, especially after the comeback of the deep learning systems in the 2010s. So things that a lot of people couldn't even imagine machine learning systems to do, like looking at an image and coming up with a meaningful caption of the image. For example, in the bottom left of your screen, you'll see a person playing the guitar, or doing things like a semantic segmentation, where every pixel of an object is classified and labeled, such as the picture of the blue van in the middle of your, in the bottom, the middle of the screen, or playing games like the game of Go, or even DeepMind's solution to the 50-year-old protein folding problem, are things that these deep learning-based systems have done exceedingly well. So much so that one can easily argue that it would have been hard, scratch that, almost impossible for even machine learning researchers to have predicted this level of performance back in 2005 or even in 2010. Now, I know many of you on the call know the differences between AI, machine learning, and deep learning systems. And so before you call me out on it, I wanted to caveat that for the rest of the presentation, I will use these terms rather loosely and interchangeably to represent a class of intelligence systems that we are all experiencing in the world today. Now, as with most good things, deep learning models come with their own set of problems. In October 2019, the journal Nature featured an article that summarized the work from a number of researchers who had shown the potential for sabotaging AI is very real. Some researchers had shown that it was possible to fool an AI system to misread a stop sign shown in the top left of your screen and to make it read almost like a speed limit sign instead by introducing stickers on the stop sign. So if you see the black and white boxes, and those would introduce this noise that can actually make the stop sign look like a speed limit sign. Other researchers had shown that it was possible to easily produce images that are completely unrecognizable to humans. But the state-of-the-art deep learning model believed it to be a recognizable object with almost like 99% confidence, such as in the bottom left, the pattern of wavy lines. To the deep learning model, it looks like a king penguin. Some scientists have also shown that it's possible to hack an image of a panda to make it look like a gibbon instead, by carefully inserting noisy pixels in the image that people would not make a big deal of, but completely deceive the deep learning system. Ultimately, the conclusion from all of these examples is that deep learning models are fundamentally brittle, brilliant at what they do, until taken into an unfamiliar territory, they break in ways that are completely unpredictable. So not surprising, when these deep learning systems move from controlled lab environment into the real world, we start seeing issues. In late 2020, a machine learning researcher named Sean McGregor started a database to invite people to contribute and proactively discover how recently deployed intelligence systems have produced unexpected outcomes in the real world. This was done in the spirit that these outcomes may help avoid making similar mistakes for people when they are doing the development of these products. Since its launch less than 1.5 years ago, more than 1,000 such incidents have been reported by researchers from companies like Intel, Google, and Microsoft. A few recent incidents from Zillow, Apple, Amazon that you may have recalled are all called out on the screen here. When we have incidents, the lawsuits are not too far behind. Here, we are trying to curate a small subset of lawsuits where different aspects of responsible AI have been called into question. in HUD v. Facebook, the US Department of Housing and Urban Development sued Facebook in March 2019, claiming that Facebook's ad tools discriminated against protected groups on the basis of race, sex, national origin, religion, etc. Similarly, question of fairness is raised in Williams v. City of Detroit, where the plaintiff is suing the Detroit Police Department for allegedly using biased facial recognition algorithm. In ACCC v. Trivago and Loomis v. Wisconsin, which we will spend more time on later on, questions of transparency and interpretability of Trivago's AI-based ranking algorithm and the risk assessment software used by the Wisconsin Department of Corrections are called into question. The BIPA cases like Vance et al. V. Microsoft or the one against Facebook that you might have read have similar issues around transparency and interpretability of AI-based recognition systems in its use of biometric identifiers. Finally, the Kumandan et al. V. Google lawsuit highlights yet another aspect of responsible AI, privacy and security, where the plaintiffs argued that Google Assistant was allegedly recording conversations even without the trigger words like, okay, Google, hello, Google, etc. So where does all of this leave us? It really brings us to a set of core principles behind a responsible AI system. Now, I won't claim to have the perfect set of principles, but I think this is a good starting point as you think carefully about your own AI system. The 6 principles include: Principle 1, inclusiveness. AI should consider all human races and experiences and address potential barriers that could unintentionally exclude people. Principle 2, fairness. Key checks and balances need to make sure that the system's decisions don't discriminate on gender, race, sexual orientation, religion, etc., towards a group or an individual. Principle 3, privacy and security. Data holders are obligated to protect the data in an AI system, and personal data needs to be secured, and it should be accessed in a way that doesn't compromise an individual's privacy. Principle 4, transparency. The model should be transparent to allow someone to understand the data and algorithms used to train the model, what transformation logic was used to apply to the data, the final model that was generated, and offer insights on how the model was originally created. Principle 5, reliability and safety. It is important for a system to perform as it was originally designed and for it to respond safely to new situations. Principle 6, accountability. People who design and deploy the AI system need to be accountable for its actions and decisions. Now, for these 6 principles to be ultimately effective, it is vital that these be supported by a strong foundation of organization and culture and a legal and regulatory framework to draw from. With this message, I want to briefly leave you in the capable hands of my colleague Junsu, who will help us understand where and how to diagnose these systems for fairness-related issues and discuss some upcoming regulations and actions that are attempting to address responsible AI. Junsu.
Great, thank you, Rohit, for that great overview. It's clear from that overview that while machine learning systems have really made immense progress in the past decade, there's also many ways in which they can fail in the real world. And there's several principles that you really need to think about to achieve responsible and robust machine learning systems. In this section, I'll focus more specifically on the principle of fairness and bias, what some of the most common sources of biases are, and also wrap up with the case study to hopefully bring all of this together with the real world example. Before we start to describe exactly where biases might occur in algorithms, let's first start off with an overview of what it takes in the first place to design and build a model. And at the start of the pipeline, as you sit down and think about the problem that you really want to solve, there's always some state of the world that you want to measure and predict. You transform that into data and then train a machine learning model on it in order to learn the data as best as possible. And then the model will take actions or predictions. For example, let's say we want to design a recommender system for a social media platform. The state of the world might be the content on the platform, the number of likes and comments on each post, other engagement metrics, and transforming all of that into some numerical data that you would train a model on. And once you have that model, in this case, the action the model takes is recommending specific pieces of content to individual users. And finally, in the case of recommender systems, there's also a feedback loop where users will engage and interact with the content that's recommended by the model. And then that's further used to actually train the model in the next iteration of updates. With that pipeline in mind, if we start to look at where biases can be introduced, it's really at any point in the pipeline. And this is also part of what makes it so easy for different types of biases to creep into a machine learning model, and also why it's so easy to overlook. We have three types of biases here on the screen: biases in measurement, in the learning process, and in the action and feedback sequence. To go over these one by one, starting with the left, we have bias that's encoded in the data itself. The clearest example of this is, let's say you want to develop an algorithm that takes in and parses resumes and CVs and ultimately decides whether you want to go forward in an interview process with the person that applied to your company. The first step in that process is to go out and collect lots of text data from the internet, essentially as much as you can. And I'm sure it's not surprising to anyone that there's going to be a lot of biases, whether explicit or implicit, out there in the internet. And the issue is that you're going to see these exact same biases reflected in the model, because a machine learning model is designed to fit the data as best as possible. And there's no reason to expect that it'll remove existing biases in the data. Next, we have bias that's introduced in the learning process. And this is where you might have a majority population and a minority population, and the two populations have different characteristics. The issue here is that most machine learning systems are trained now and over the past decade, they'll naturally optimize to fit the data as best as possible for the majority population. And that's fine to do until the populations have different characteristics, and that will lead to biases for the minority population. And in the next couple of slides, we'll do an example of what that looks like. But finally, there's also bias in the action and feedback sequence. And this is the example that we went over earlier with designing a recommender system for a social media platform. And this type of bias happens when the data that's used to train a model depends on the output of the same model. And that's clearly the case in recommender systems where users only get to engage with the content that's recommended by an algorithm. And then that engagement data is fed back into the model to train it. And what happens with these types of feedback loops is that algorithms will very quickly fall into a narrow space where it continues to recommend the same type of content to a specific user. And this will lead to things like echo chambers and filter bubbles. I wanted to come back to this second example of bias and walk through a quick example to demonstrate how and why bias can occur in the learning process itself, because it's not obvious why that happens and how that's different from bias that's encoded in data. There's an illustrative example of this on the right side of the screen, which shows a very simple machine learning model. And what we want to do with this model is to predict success after college. And we can use any metric that we want. For example, we could look at income levels 5 years after graduation. And this model is going to take in two inputs: the SAT score, which is on the y-axis here, and the GPA scores, which is on the x-axis. In terms of the data points that are actually plotted on the graph, the pluses indicate students that we've been able to track and know that they were successful based on that metric, and the minuses were the students that were less successful. And with the setup, the objective of the model is to really just draw a line through the data to be able to separate out the pluses and the minuses as best as possible. And we see an example of that here for population 1, which is the majority population in this example. If we flip to the minority population or population 2, we see something interesting, and that's that the SAT scores have shifted down. And there might be a couple of reasons why that's the case. For example, the majority population might be from a higher income group, and so they can take the SAT exams multiple times and report the highest score. And they also might have access to additional resources to help prepare for the exam, whereas the minority population might be from a lower income group and not have access to the same resources. And so we see that there are different distributions for the features for the minority and the majority populations that are being fed into the model. And this seems okay until you combine all the data for the minority and the majority population into one data set and train a machine learning model on it. And this is because the machine learning model is being trained across the entire data set. And by definition, the weight it places on the majority population will be much higher than the weight it places on the minority population. In this very simplified example, you see that the final decision boundary, or the machine learning model that learned from this data, sets the line such that it's very unfair to the minority population. It's essentially saying that every person in the minority population will not be successful after college. And even though the model is making a couple of mistakes, ultimately it doesn't quite matter to the model because it's such a small number of students relative to all the data points that it's trying to optimize over. And one question here might be, why not just train 2 separate models for each population? From a technical point of view, that seems like a good thing to do because you'll have 2 models, they're both accurate, and that seems a lot fairer than having this one model across the populations. But one of the issue here is that in many cases, companies will not be able to do that, especially for higher risk use cases, because that means they actually have to go out and collect data on protected attributes and then explicitly use that to make decisions based on the protected attributes. And that's not okay to do under certain regulations. And this is also an example of there being a conflict between the technical machine learning research community and existing regulations, because companies don't want to go out and take on the risks of doing something like that. So we've talked through 3 common sources of bias that can come up in the design of machine learning models. I want to bring all of this together with an example and highlight some of the complexities and nuances that can happen in the real world. And this is an example where you actually see all 3 types of biases that happen together, which makes it so difficult to fix later on once you have it deployed into production. And I'm sure a lot of people have heard of COMPAS, and it's really the hallmark example of bias in algorithms. As a quick overview, COMPAS is a statistical model that was developed by Northpoint in order to predict recidivism risk. And that's the risk that if you were to release a criminal defendant, would they re-offend? Would they go out and commit another crime? And this model is already used widely in the US in the criminal justice system. And it really doesn't get to be higher stakes than predicting recidivism and being an input to sentencing decisions. There's several nuances that make this COMPAS example an interesting one. The first is all of the debate around which metric to use. On the bottom left of the screen here, you see something called calibration. And that was what Northpoint, the developer of the software, was pointing to and putting forth as the metric to care about for fairness. And calibration is a very simple metric. It means that the algorithm, if it gives a defendant a risk score of 7, then there's around a 70% chance of the defendant recidivating. And that's well calibrated across the groups. So regardless of whether you're a Black defendant or a white defendant, If you get a risk score of 7, it means the same thing. And that seems like a perfectly reasonable definition of fairness. On the other hand, what ProPublica pointed out was that you actually need to look at where the algorithm was making mistakes and what type of mistakes across different groups. So we have 2 sets of bar charts on the right here. And starting with the left side, that was the type of error where the algorithm was labeling defendants as higher risk, but the defendants didn't go on to reoffend. So that was a mistake. But if you look at the data, it says the algorithm makes this type of error twice more frequently for Black defendants than for white defendants. And on the flip side, you see the algorithm also makes a different type of mistake where it labels defendants as lower risk, but they do go ahead and when they're released, they do reoffend. And so what the Compass software was doing was it was making roughly the same number of mistakes for Black defendants and white defendants, but the type of mistake they were making were different. And that certainly feels unfair for Black defendants. What this also told us was that definitions of fairness matter. And you need to think about what type of fairness you want to optimize for, because in many cases, it's not technically possible to optimize for all types of fairness to the same extent. And taking this a step further, you also need to think about the stakeholders involved, because different metrics matter to different stakeholders. So from the perspective of the judge, it seems like calibration is a great thing to have because you can look at solely the risk score and know what it means, and you don't have to think about race or ethnicity or what group the defendant is in. From the perspective of Black defendants, and especially a defendant that knows that they're not going to go out and reoffend, then that type of error is going to be the most important to them. And then finally, maybe from the point of view of the local neighborhood or society in general, the final type of error, that metric might be the most important because those are cases where people are being wrongly labeled as lower risk and being released out from the prison system. So we've gone over several common sources of bias and a case study that shows why bias can often be nuanced and hard to define. Next, I'll spend a couple of minutes hopefully providing some light and hope on what we can do in terms of going forward and the upcoming regulation and how to think about ensuring and designing fair and robust machine learning systems. And even if you do a brief review of the landscape, it's clear that there's a lot of regulatory effort that's going into thinking about algorithmic accountability. And this is across the globe, including the US, both at the federal level and the state level, in Europe, in China, Singapore, and across the world. And we have just a select set of these here. And starting with from the left, there's the EU Artificial Intelligence Act. And this was the act that introduced a risk-based framework for regulation enforcement. And you have this pyramid of criticality on the bottom. And on the top of the pyramid, you have things that are unacceptable risk. And so for those things, it would just be outright banned from the market. On the other side of the spectrum of the pyramid, you have things that are minimal risk, and you don't have to worry as much about the risks that are happening in those applications. And in the middle are going to be the things that are a little bit hard to think about, things that range from limited risk to higher risk. And depending on the level of risk, there would be a different set of regulations that apply. The second is the Algorithmic Accountability Act of 2022. And this was actually an updated version of the same act that was proposed 3 years ago in 2019. And what this would require is a certain set of companies that are big enough based on some metric, like the number of users, to conduct impact assessments for algorithmic systems. And it defines what needs to go into an impact assessment of algorithms. And ultimately, if this act were to be passed, it would require the FTC to create regulations around it and also to collect documentation and the reports from the various companies and then publish, aggregate, report on the trends at an annual basis. Finally, we have the New York City law on automated employment decision tools. This was actually passed into law and goes into effect January 1st, 2023. And while we won't go into the details of this here, companies that use automated decision tools for making employment decisions really need to start thinking about bias audits and how they want to go about that process. Finally, to wrap up, it's clear that machine learning systems have an outsized impact, and they're already being deployed widely in high-risk use cases. Bias is also subtle and hard to define because the reasons why bias can occur can be nuanced in the real world. And while there's been an immense amount of progress in machine learning, the way most models are trained nowadays typically just optimize for a single metric like accuracy. And so things like fairness and interpretability are not top of mind for many machine learning developers and companies. So what can we do to design and ensure fair and robust machine learning systems? We have a couple of items on the bottom of the screen here. And first is that for high-risk applications, machine learning systems have to be explainable, transparent, and auditable. And that means having an auditable trail of the data that was used to train and test the model itself and associated configuration files, as well as rigorous documentation about the team that was involved in developing the model and what the objective of the model was. It's also not simply about training a fair machine learning model once and then deploying it, putting it into production and forgetting about it. It's as important, if not more important, to have continuous monitoring systems in place to be able to monitor if the model is continuing to be fair and if there's any discrepancies in the post-deployment stage. Third is that fairness will always have a social component. Machine learning models are developed by people and they impact real people out there in the world. And it's not going to be possible to automate away the social elements in this process. And some parts of it will always require human input. And finally, as we talked a little bit about, we think well-thought regulation is required and critical to guide AI deployments in high-risk applications. And this will allow companies and organizations to both innovate and take advantage of emerging technologies like machine learning, but also balance it and manage the risks to consumers. And with that, I'll hand it back over to Emily for Q&A.
Fantastic. Thank you, Junsu, and thank you, Rohit. So we received a few questions prior to this webinar as well as during. So we're going to try to get through as many as we can now with the next 5 or 10 minutes or so. And if you do have any other questions, feel free to add them in the Q&A box and we'll try to get to them. So Rohit, this first one's for you. So the question was, do we need to have a global set of standards for responsible AI?
Okay, this is a tough one. Let me start by sort of like saying that there have been a lot of movements in trying to develop national and global policies for AI. Last I read, there were like 60 countries that had adopted some form of AI policy. And many international bodies have been working very hard on the technical aspects, the ethical aspects, and the policy aspects of responsible AI. The G7 in 2018 had established some kind of a global partnership on AI. There's an OECD initiative. So lots and lots of initiatives to work towards like forming a global set of standards. But while we recognize all the benefits of having this type of a global set of standards, coming up with one that'll work for everyone is going to be very, very hard. I mean, now there's good news that there's general global consensus around the 6 principles of AI that we discussed today. But how we go about implementing them is where the issues will probably arise. Now, with different risk tolerances among different countries and people, and like the diversity of thinking, it is not surprising that implementing something that will satisfy everyone is almost going to be impossible. Even when you think about implementing the simple fairness principle, coming up with the common set of dimensions like race, country of origin, gender will be extremely difficult. Having said that, it's going to be tough. I do believe that when it comes to regulation, having some sort of global set of standards will be helpful. We already know that like having divergent approaches can create barriers to innovation and diffusion. Take, for example, all the data policy restrictions between countries, and data being an important ingredient towards any machine learning model. So actively reducing or working towards reducing these barriers through cooperative talks and discussions will be important. And I think that's where the global set of standards for responsible AI will need to be developed. And so I do think there is a very strong need, but the devils are in the details, unfortunately.
Yeah, always. Okay, thanks, Rohit. So another question that we got, this is for you, Junsu. So the question was, how do you think about the trade-off between personalization and fairness? And maybe you can speak a little bit more generally to trade-offs.
Yeah, that's a great question. And if you start looking at fairness in machine learning systems, it's clear that it's all about trade-offs. So even within fairness, you have something like 21 definitions of fairness that you need to think about, and which ones do you need to prioritize. And there's a lot of, this is actually an active field of research right now, so I won't have all the answers, but there are trade-offs between accuracy and fairness and privacy. So once you start really getting into the details of how to operationalize these models and the concepts of fairness, you do really need to start thinking about the different trade-offs. And with that being said, I think there are also trade-offs that have had a lot of debate around like the accuracy versus fairness trade-off. And it was taken sort of as to be truth that if you want increased fairness, you need to sacrifice accuracy. But a lot of research in the past couple of years, 1 or 2 years, has shown that that's actually not true. And in many cases, you can get increased fairness without sacrificing a lot or even any amount of accuracy. And there's really a lot of research around this. So it's a constantly evolving field. And I think anyone that's sort of interested in the space has to keep tabs on it. But I do think the story in general is that trade-offs is very, very important to think about when you're designing a robust and responsible machine learning system.
That's great. Thanks, Junsu. Okay, so this was a popular question. And Junsu, I'm going to pass it again to you. Is there a checklist to identify bias? What can lawyers, litigators, regulatory individuals do to identify bias in these cases?
Yes. So there are checklists out there, and a lot of different organizations have thought a lot about a checklist, essentially a set of things to go through to identify bias and mitigate it. Microsoft does a lot of great work in this space. They have a responsible AI checklist. There's also different checklists for different domains. So there's a algorithmic bias playbook, I believe, from Chicago Boot, and that's centered around how you think about bias in healthcare in general. And then there's also the latest really set of exciting things that were published in the last month or so was from NIST, the National Institute of Standard and Technology. And they actually published a publication thinking about how to develop standards for identifying and managing bias in AI. And they actually published this just last month. And they're also actively working on a AI risk management framework, and they have a first draft of that out. And so there's great resources that are out there. And I think these resources will all give you a great starting point. But also, given everything that we've talked about, I think fairness and bias and responsible AI is very context specific. So it depends which country you're in, what use case you're developing it for, what domain you're in as well. So while these will give you a great start in terms of thinking about how to identify and mitigate bias, ultimately you'll have to really put in the effort to apply it to your specific use case. And I think that will always be true in designing responsible machine learning systems.
That's great. Thanks, Junsu. And to that point, so we'll be sending around some follow-up materials and resources to everyone who was able to attend today, as well as those who couldn't attend. That way you'll be able to kind of see some of these checklists, additional resources, research that you'll be able to learn from as kind of the next step in today's learnings. And so we have a few more questions to get through. We just have a few more minutes here, but I think the last one we'll end with is, again, for you, Junsu, Rohit, feel free to jump in if you'd like. So how do you think about the role of interoperability and how this factors into the process?
I do think interpretability and explainability are very important things to think about. And there's also the distinction of, do you want to develop explainable models? So things that are less complicated. And in cases where you can get a similar amount of accuracy with a less complicated model, I think it makes much more sense to develop these explainable glass box models. And then there's a whole set of tools out there where, for example, for face recognition, you do need to just use a much more complicated neural network-based model in order to be able to do much better than these other traditional methods. And there's a whole suite of tools out there that allow you to do post hoc explanations and figure out how the model works under the hood. I do think interpretability, this post hoc interpretability, is the domain where it's least well defined. So there's a lot of different methods out there. And if you apply different interpretability methods to the same data set, the same model, you actually get different answers as to what the model is looking at. And a lot of the past couple of years in the interpretability research space has been pointing out that previous research methods do not work and they're not robust for some reason. And so I think it takes a lot of upfront thinking in terms of how you want to apply these interpretability methods and making sure that you can trust them. Because right now, a lot of the best practice is going to some off-the-shelf tool like SHAP and then applying it and looking at the outputs and sort of blindly trusting the outputs of that. But I think in order to have a more rigorous process around it, you need to really understand what the algorithm is doing and if it makes sense for your use case and the model.
I just wanted to jump in quickly. I really want to emphasize and underscore the importance of explainability that Junsu sort of like mentioned. It is really an important aspect of earning trust in these systems. I mean, as you sort of like think about AI being used in healthcare applications and medicines and places like that, where if you get a report coming out from an AI system, you really like to understand if that report is really telling you what it should be telling you. You really need to have an intuition of what's going on in the model. And currently the models are quite a bit of a black box and very hard to interpret. And so that explainability is a critical element here that needs to be worked on and will actually be an important area to develop in order to reduce the barrier for all of these models to be actually used in the real world application.
Got it. Thanks, Rohit, for jumping in there. So we are at time. So I just want to thank everyone who joined us today for this session on responsible AI and the legal implications of bias in algorithms. So I know that we had a mix of folks here on the webinar, including some litigators and other professionals in tangential fields. So we'll be sure to send some follow-up where appropriate, especially for those folks whose questions we couldn't answer today. We'll make sure to send one-on-one notes, make sure that those questions are answered after the fact, and feel free to email Junsu or Rohit. Their emails are listed here if you do have any specific questions. We're more than happy to schedule some time to meet if you guys do have any questions for cases that you're working on, or any other general questions you may have. So feel free to follow us on social media. Also check out our website for more information at www.keystone.ai. But otherwise, thanks again for your time here today. We really appreciate it. And let us know if you have any feedback or further questions. Okay, have a great rest of your day, everyone. Bye-bye.
Thank you. Bye-bye.